lot of parameters. So we're not going to get into that. But which one would you use? Most people are going to say dynamic, and the answer is no. It is use static values in designing the fracture. Why is that? Well, the dynamic values is actually you are vibrating the grain, but when you look at your fracture, although the fracture is obviously a dynamic process, but it is not depending on vibrating the grain, is actually pushing the rock very much like what you do in experiment. And so what we would do is you develop a relationship between the dynamic and the static properties in your formation. It's easier to run logs. So you run the logs, take the values, and boom, through your correlation between static and dynamic, you get the static and use that in designing the fracture. Okay? I may have said it a little fast, so you may want to listen to the game. So here is the stresses. Now, this area is a little dry, I have to admit, but it's important to understand. So now what stress would you use? Well, the stresses that you have, the total stress is carried by both the grains, sandy grains, and by the fluid. Okay. So and what is affecting the propagation or sanding or collapse of the rock is the effective stress, not the total stress. Effective is because the stress is being carried by both the grains and by pore pressure. The first attempt to do that, to look at it, was Terzaki's effective stress. He said, hey, what is being carried by the grains is you just take the total stress and subtract out of it your pore pressure. However, people found out later on that pore pressure may not be 100% effective in carrying that stress because it moves out as you press it, it moves out. So, and they say, well, there is a factor here that it is usually less than 1, which will Biot coefficient. So rather than assuming it's 100% efficient, using partly efficient. So that's the Biot constant anywhere between 0.7 to 1. It depends. Most people will probably use about 0.9 or so. But it is important to measure that parameters, especially if you're going to look at sanding. That is very important to do. So you can see in some situation your Biot constant for Ottawa sand, porosity, if it is dry, is 0.33. You can see that's in megapascal. If you want to relate to it, this is megapascal is 10 atmospheres. So you multiply any of those numbers by about 145. 1 atmosphere is 0.1 megapascal. And so you can see there is, depending on the rock, it may be up to 0.9, and in some rocks it may be down less than 0.5. So it's important to test the rock. You can only find it by testing. You test the rock and you find what Biot constant, Biot coefficient you have, because that's going to affect your sanding issue. So we've done that. This is just a table to give you specific gravity of different material in case important in case you get a problem on calculating that stress. So freshwater is 1. This your specific gravity is dimensionless. So to get the stress downhole is the depth, the integration of the depth time times specific gravity times 0.433, which is the gradient of fresh water. So in case of quartz is about 2.65, so 0.433 times 2.65, it gives you whatever value is a little bit more than 1 psi per foot. Now, without going into, let me look at the first equation. I usually we go through the derivation of this equation, which is very easy to do. And my advice is you go, if you Google it, you'll find the derivation. Derivation is very simple. Basically, all you're saying is that when we calculate Poisson's ratio, we're saying it's unconfined, and we calculate how much lateral strain you have. But if that rock, where you're applying stress, is part of a huge formation, then it doesn't have room to expand. Then it's applying stress. So Poisson's ratio also is saying when I apply stress vertically, part of it is going to transfer horizontally. And so if I apply this concept, then I can say when I apply effective stress vertically, which is sigma V dash, there will be sigma H dash. There will be a horizontal stress, effective horizontal stress moving sideways. The relationship between the two is based on Poisson's ratio. Okay, and so you can see Poisson's ratio has to be less than 0.5, because if Poisson's ratio is 0.5, that's saying the stress is transferred horizontally 100%, that the rock cannot carry any stress, which obviously that is false. So if the rock can carry some stress, then Poisson's ratio has to be less than 0.5. In sandstone, it may be 0.35 or so. So you can look at it and say 0.35 divided by 0.65, so it's a little bit more than half the effective vertical stress. Okay, in case of shale, if it's softer shale, it may be 0.4, a little higher than 0.4, not much higher. Sandstone maybe even less than 0.35, maybe 0.3. So you can see that this is the reason that the softer shale will have higher horizontal stress than hard rock, sandstone. And this, as we are going to talk about next week, this provide us with some confinement of hydraulic fracturing. So nature was nice to fracturing, to the oil industry, to create fractures that are somewhat confined. We'll talk more about that next week. And so here I'm just giving you this equation that I usually ask students to derive. You can see in the first equation is the relationship that very easy to derive. You may want to Google it. I may add the derivation to the presentation that will put it in ResearchGate, and we send you a link of the last week presentation. You're going to receive another link for this week's presentation. Then if I substitute the definition of the effective stress, I end getting here an equation relating the total horizontal stress to the total vertical stress, and obviously pore pressure will appear, and also alpha would appear. If we're in class, I would have asked you if you remember what alpha is. It is Bytes constant. In situ stress orientation is very important. There is multiple techniques to calculate it. That will, let us wait till when we talk about testing next week. There's a lot of ways to do it. And next week we'll talk about the microfrac testing. I may add something about, I was not planning on it, but an elastic strain relaxation. This is something that's very interesting that we have done previously. We'll talk about it next week. We probably will not talk about tiltimeters. It's been used before. It's very interesting technique, but we may be able to. Then people will use well testing and doing it. Geological rules of thumb. I have personally used that. We work with a company, and the company was not they really did not want to run any testing. Say, well, can you guess what it would be from our geologic map? I looked at it and they said, yes, yeah, we can do that. You look at it, it was an anticline. There was already long natural fractures. There was faults in the formation. So it would be parallel to the hydraulic fracture. Most probably would be parallel to this fault. So you follow the anticline. And so that is one way of doing it. Let me look at the effect of drilling a well bore, because this is something I will cover before we. It is fairly important to understand the breakdown of a well bore to create a fracture. So when you drill a well, I should have had a graph here. When I drill a well bore, I change all the stresses around that well bore. Okay. Many years ago, this equation was developed. When I say many, if you know mathematics is more advanced than any other technology. People develop stuff in math that takes many years before it gets applied. So if I have a rock, and let me show you, basically I did that by hand a couple of days, or actually over the weekend. If I have drill a well bore like this, and the minimum stress is this way, the minimum horizontal stress, the maximum horizontal stress is in the other way, and I'm looking at the top of the well bore. So the vertical stress is going vertically into the picture. And I'm going to look at an angle of theta here. So I can look at any point in the reservoir, not inside the well bore. Any point inside this reservoir, this is the white area is my reservoir. And if I draw a straight line to the center of the well bore, I have this angle theta. So the stress at any point inside this reservoir is defined by these two equations. So sigma RR is whatever stress that is going perpendicular, going towards the center of the well bore. Sigma theta is the stress adjacent or tangential to the well bore, or parallel to that well bore. So you can see it is moving like a circle around this well bore. So this equation would describe, so now you know the definition of sigma H, sigma H max, and the theta. RW is the well bore radius, and the R is whatever distance you are away from that well bore, from the center of the well bore. So I'm going to do it just mentally here, rather than, usually it would be, I want you to, it may be a good exercise for you to eventually sit down with a piece of paper. I'm going to do it very quickly here. So the first question here is what what is sigma RR at the well bore without looking at the equation. Well, sigma RR at the well bore, if the well bore is stable, should be 0. So let us substitute here. So at the well bore, RW is equal R. So this is 1. 1 minus 1 is 0. So the first term disappears. And here was 1 minus 4 times 1 plus 3 times 1. So that is again 1 minus 4 plus 3. That is 0. So the second term is 0. So sigma RR at the well bore is 0 regardless of theta. So that's now I have a stable well. If it is not stable, we'll find out later on. Maybe next week we'll talk about testing. We'll see other situations. So sigma R is regardless of theta at the well bore, it is 0. That sounds very good. So now let us look at sigma theta theta, which is tangential to the well bore. So at the well bore, RW square divided by R. Well, R is equal to RW, then this is 1. 1 plus 1 is 2. 2 here cancels out, so I end up having with sigma H plus sigma H max minus this second term. I'm going to do it now for theta equals 0 and theta equal 90 degrees. Okay, so everyone get a piece of paper and follow what I'm saying. So at R equal RW, so I have sigma H plus sigma H max minus, this is 1 plus 3 is 4, then it becomes a minus. I'm going to open parentheses, 2 sigma H minus 2 sigma H max time cosine. If I'm at 0, cosine 0 is 1. So when I put this all together, it ends being 3 sigma H max minus sigma H min, right? Okay. Now I'm going to do the same thing again, except I'm going to put theta of pi over 2, 90 degrees. So pi over 2 times 2, that's pi, that's 180 degrees. What is cosine 180 degrees? I hope you remember it is minus 1. And so if I put that, now multiply that second quantity by minus 1, I will find out at 90 degrees, the equation is fairly similar. It is sigma 3 sigma H min minus sigma H max. Okay? Remember that, because this equation, I will be asking you if you know anything about hydraulic fraction, you remember the CFD definition and you remember this equation too, as well as the equation for Poisson's ratio, the relationship between the vertical and minimum horizontal stress. There's 3 equations you need to remember. So if I look in here, I find out the sigma RR at this, at theta equal to 0 is 3 sigma H max minus sigma H min. And at 90 degrees, which would be vertical here, the sigma theta would be vertical. It is 3 sigma H min minus sigma H max. Now, if I'm ballooning, if I'm injecting fluid and I'm getting this well to expand, to get a little bigger, where would it break? It would break at this point where it has the smallest stress, because what I find out that this will be the smallest stress here and the high, talk about tangential stress, and this is the highest tangential stress there. So fracture is going to break here and propagate perpendicular to minimum stress. that is the way it should happen. I look at the breakdown pressure, and it looks something like that. So sigma RR at the wellbore, regardless of where you are, this is sigma RR, is 0, and when you go away, it goes back to the far field stress. Sigma theta theta depends on your orientation. So if I have a graph like this, which sometimes people call it hoop stress. So hoop stress, here is the largest, here is the smallest. So it depends. So if I'm ballooning the fracture, it will break at the smallest value. There are a lot more to it, because as you fracture the well, you change that stress regime. So here I'm saying this is wellbore that has not been fractured yet. So I apply stress, it should look something like this. If I increase the stress, eventually it will break at theta equal 90 degrees. It's in here, like what we show. So the fracture will propagate this way, perpendicular to minimum stress. How about breakdown? Have you ever looked at a formation and you notice it's breaking down? Well, when breakdown is under compression, so actually breakdown will happen in this orientation, because now I have very high maximum stress. It's causing the formation and lowering the pressure inside the wellbore very much, that you have a breakdown here and here. Then if I look at a breakdown, I know immediately that the minimum stress is in the other direction. I mean, the minimum stress this way, so the fracture is in the other direction. So how to take care of it is you increase the weight of the mud. And here is the equation considering the pore pressure and the depletion of the formation. So here I have wellbore pressure, and I have pore pressure, and obviously here you'll be considering Bright's constant. So what equation you would remember? You wanna remember? Let's go back to this equation. You want to remember not this whole equation, but you want to remember the 3 sigma max minus sigma h, because that appears very much. You want to make it more accurate, you add the tensile strength to it. You want to remember CFD, and you want to remember the Poisson's ratio. So let us entertain a couple of questions. Again, I'm going to put this presentation on ResearchGate. We'll send the link to Dr. Al-Garhi, who will communicate with you. But you don't actually even need the link. If you know what ResearchGate is, you can get on it and you can download anything you want, assuming it isn't there. I've sent also, Dr. Al-Garhi would send you a link to some write-up I did. It's a long time ago, in mid-90s, early to mid-90s. However, it is still a very good write-up. It's mostly for fracturing horizontal wells, and I would suggest that you read it for your own enjoyment. Anyway, let's entertain a couple of questions.
Okay, so thank you, Dr. Soliman, for this informative session. Now we will begin by addressing the questions. So the first question is that should we drill the horizontal wells in the direction of minimum horizontal stress direction, and why?
That's a good question. Actually, drilling a well in direction of minimum stress, we found out if you have normal stress regime, actually this is the most stable situation you've got. So, second, we don't have, I don't have a presentation on that. Well, I do have in my computer, but not in here. People always talk about what is the optimum or the best way to deplete a formation. You want to drill horizontal well and fracture it, usually in very tight formation. And the best way to do that in a tight formation is to create multiple fractures in that horizontal wells. If we look at history of what we have done, we started, and the first fracture of the horizontal well was in late 80s. Actually, I do have a paper on the subject you can download from SPE that I wrote back in, presented it in 88, and it was published in 1990. Well, I can't send you a link of it because SPE owns the copyright. So you have to download it from SPE. And so we used to talk about 4 to 6 wells. Now we fracture not even 10 or 20, sometimes 100 fractures in one horizontal well because the formation is extremely tight. You can't, you can do that only with horizontal well where you create multiple fractures. If we have time at the end, I will show you. Actually, I do have a nice presentation on that we did 8-10 years ago. I may put it also in ResearchGate because it is my presentation. I cannot put papers, but I would put it in ResearchGate. Look at it. It's a very interesting presentation, and it deals only with fracturing horizontal wells. And that usually I used to cover it. It's only mostly about fluid flow, and it used to take me about 3 hours to present. But we'll put the presentation. You may wanna look at it.
Okay, great.
Sometimes in the future we may present it to the group in the distant future. Go ahead.
Okay, great. Thank you. And the second question is that, is it possible to see hydraulic fractures in real life? And if yes, is there any real example for that?
You see it real life?
Yes, I think he means if it's visible, like to see it in the naked eye.
No, not visible.
Horizontal fractures.
But let me say something about that. We have many years ago, when I was in the Halliburton company, Halliburton developed a tool. I was involved in it. There was a lot of people were involved in that specific tool, and it was a joint project between Halliburton and Total, and it was called the tool, THE, for Total Halliburton extensometer. And basically, we worked on. Myself and my group, we worked on the rock mechanics side of it, and there was other groups working on the electrical part, another group working on mechanical part, where you go in and you inject the fluid and you balloon the well, so you don't observe it by eye, but you observe the behavior of ballooning of the fracture of the well bore, and eventually you observe or measure the behavior of the fracturing process and the widening of the fracture.
Dr. Soliman, I believe the question mean instead of having vertical fracture, he's talking about horizontal fracture. Is it a real cases that we see horizontal fractures in real life?
Did he say horizontal fracture? Or?
Yes, horizontal fractures, yes.
Well, I have seen cases. At least there was one very clear case where it was a horizontal fracture. I have another case that you don't, let's not say see, but observe the behavior of horizontal fracture. We've seen that. It's not very common, but we have seen it. Yes, it can be done in a vertical well. You see horizontal fracture.
Okay, great. Thank you. And the last question for today, can we use the dynamic Young's modulus to design a hydraulic fracturing operation or job without converting it to static Young's modulus?
The answer is no. Yes, you need to convert it to the static values. Many people have written, there have been a lot of correlations. You have to build the correlation based on your reservoir. So many people have done that. You can't just, there is no general relationship between the two. It has to be developed for a reservoir or a basin.
Okay. So thank you, Dr. Soliman, for joining us this afternoon, and we were a pleasure to have you today. And I just want to highlight that